Okay, good. All right, so we're going to start the class today by going through the inequality and linear programming classwork that we did on Wednesday. I must say that the responses were much better this week than last week. Still intend to get 100% response. In other words, I want all students to send their solutions. Still not getting solutions from some persons. And some persons sending their solutions too late. Some persons sending their solutions Saturday night and Sunday morning. That can't work, right? When you get the classwork on Wednesday, I need to get those solutions by Thursday, Friday the latest. That way I can go through it, I can communicate with you, right? And we can look at where you're making mistakes. Persons who do the classwork will tell you that we communicate a lot, one-on-one, right? Some persons have even sent additional questions for them to do, right? And they have actually completed those additional questions. So they are growing, they are benefiting from the interaction that we have. So the more questions, the quicker you do the classwork, right? The much better I'm able to help you. As if you finish your classwork and I say that, okay, you're on track, then I can send additional questions for you to practice and get additional practice. And then you grow in the subject and you grow in the topic, right? So, some persons have already done 3 and 4 additional questions, while some of you still not yet finished with the very first question, right? And you don't have to stay home and toil over it, Just do what you think you're supposed to do and send it to me. I tell you, I don't care if it is right or wrong. Just send what you think you're supposed to do to me, and I'll take it from there. If I just need to make a note and send it back to you, I'll just make a note and send it back to you. If I need to make a call and call you and talk to you, I'll do that. If I need to have a one-on-one Zoom session with you, I'll do that. I've done that for students just this last week. I've had one-on-one Zoom sessions with some students who need that, right? As I say, some persons have done 3 and 4 additional linear programming questions, right? So I need that. I want all students to benefit to that same level, to that same extent. But it starts with you doing your work and you doing the classwork and sending your solutions. I can only react to what you do, right? I teach a lesson and then I give you the work, and then it is up to you. What happens next depends on you. You are the catalyst of what happens next. So the more work you do, the more work I will do with you. If you do 0 work, then I can't do anything. I'm going to end up doing 0 work with you. So the students who communicate with me the most and send the most work to me for me to do, they are the ones who are benefiting more. And guess what? Nobody paying the same money, So it don't make any sense. Why should you and somebody be paying the same money? One person get 10 hours of my time and you want to get half an hour. That don't make any sense. Everybody can get the same amount of time. Everybody can get the amount of time that they need. I'm prepared to give each student the amount of time that they need. So if a student only needs 1 hour, then you'll get the 1 hour. If a student needs 10 hours, I'm prepared to give the student the 10 hours. I'll find some way, somehow, of giving the student that time. Right? And I don't want to have to be going back. Because when we move on from this topic today, I don't intend to go back to this topic until we are revising. We're going to have a period of revision after we finish vectors. Right? So we're going to be doing matrices today. Then we're going to be doing transformation. Then we're going to be doing vectors. And then we're going to have a revision of everything that we have done since we started. And then when we finish that revision, then we will continue with trigonometry. And then we'll move on in the syllabus. All right? So that is the plan. And just stick to the plan and everybody will be fine. Just work with the plan. This is not a random thing, This is not an arbitrary process. Right? Everything is strategic. Everything we do here is strategic. So you just need to do your part. Do the work, send it to me, and I will take it from there. That is how you get the attention that you individually need to get by doing the work. All right, so let's go. All right, so this was a classwork, and what I'll do, I'll try to explain it the best way possible, specifically for the benefit of those who are not here, and for those who continue to struggle on the topic. And the reason why you're struggling on the topic is simply because you're not practicing. I'm telling you. All right. And I always say to the students, do the exact questions. Do the same question that I do in the class. Do those questions first. And I'm realizing that people not doing that by your solutions and by the questions that you ask. Because if you do the exact same question that I do in the class, then there are certain things you pick up right away. So even after I do this question today, especially persons who did not do it or persons who did not get it correct, you need to go and redo the question even after I do it today. So even though our topic for today is matrices, you still need to go and do this question if you did not do it or if you did not get it correct. All right, so that is the plan. All right. So the first question there is to solve that. Yes?
That's not the question he gave us to do.
It's not the question. Of course, this is the question. You don't
No,
look
sir.
like it. Yes, it is. This was the first one. I gave you two questions. I gave you this one, and then I gave you that one with the phones and the radios. Don't it?
Okay.
Huh? So you're telling me what I gave you? I'm the teacher. I know what I give you. I gave you this first. That was the two questions I got to know. Just that most persons were focusing on that one. But this was the first question. All right? So that was it. All right. So we're doing question one first. And it is simply to solve that inequality. That's a linear inequality. Why we call it a linear inequality? Because the power of the unknown variable, is just x, is just a 1. Right? So the power of the unknown variable here and here is 1. But if it had an x squared in it, then it will be what we call a quadratic inequality. If there are x squared term in it and the inequality sign is a quadratic inequality. And the approach to doing the quadratic ones are different. All right? So we're talking about the linear type. And as I said to you, to solve the linear type, x minus 3 less than 3x minus 7, basically is the same procedures, same steps as if you were solving the equation x minus 3 equals 3x minus 7. Same steps. The only difference with this one is that if there comes a point when you have to multiply or divide by a negative number, you have to reverse the inequality sign. That's the only difference, you know. So it's the same steps. I'm not telling you that you're to do both of them. I'm not telling you to do this and to do this. I'm not telling you that. I'm just telling you that it's basically the same steps. You're trying to make x a subject. So the same steps that you'll use to make x a subject of that one is the same steps for this one. The only difference with this one, as I said, you have to reverse the inequality sign if you ever have to divide or multiply by a negative number. All right? So let's look at it. If I was solving this one over here, what would I do? I would try to group the x on one side, and I can decide to group the x on this side, or I can decide to group the x on this side. Anyone, I can decide either one. Now let's say I'm going to group the x on this side to make it a subject. It will be x. Mute your mics, please. It will be x minus 3x. When I bring it over this side, it becomes 3x. And then that will be left with negative 7 on that side. So don't change the sign. It is negative 7. And then this negative 3 will go over here and become positive 3. Positive 3. So essentially, it's the same as saying subtract 3x from both sides and add 3 to both sides. It's the same effect, you know, but the shortcut way is to say we carry it over the next side and change the sign. All right? So we did not multiply or divide here. So this becomes negative 2x and this becomes negative 4. And the next step now would have to be to divide by the negative 2. So when you divide by negative 2, you would get x equals negative 4 over negative 2. And so the x would just be equal to 2. Just like that. So let's look at the inequality one now. Right? The other option, you know, was actually to group the x values on this side. So let's do it that way as well. So let's do it that way. Because some person did that. 3x minus 7. So if we group in the x on this side, we're taking this over here, and we're taking the negative 7 over there. All right. So what we would get is this side becomes 3x minus x, and this side becomes 7 minus 3. And the negative 7 goes over here and becomes positive 7. and the x here goes over here and becomes negative x. Note that this negative 3 stays as negative 3. Some persons have a habit of changing it to a plus. All right, and then this side becomes 4. And then we basically divide by the 2. So if you divide both sides by 2 again, you're going to get x equals 2. So x2 equals x is the same as x equals 2. So we can say i.e. x equals 2. All right, so that's if we're solving the equation. But this is not what the question wanted you to do. And we're showing you that it's the same steps that you would follow. The only difference is that in this one, you have to reverse the inequality sign. All right, so what we would have to do to solve this now? Same thing again. Group the x values on the same side. So let's say I'm transferring to this side first. I'm going to take this over here, and it will become negative 3x. And I'm going to take this over there, and it becomes positive 3. All right, so I would get x minus 2x. The sign remains less than. This is negative 7. Don't change it to a positive 7. It remains negative 7. And then this negative 3, when it goes over here, it becomes positive 3. So I get positive 3. So you realize it's basically the same steps as that. Now this is supposed to be a 3x, 3x. All right, this is 3x. Right, so you see the same thing, right? Same thing. The only difference now is that we have an inequality sign here. All right, so far we have the same thing. All right, then now this becomes negative 2x less than, this becomes negative 4, because negative 7 plus 3 is negative 4. And then now we have to divide by the negative 2. To leave x as a subject, we have to divide by this negative 2. I like to divide both sides by negative 2. All right, but the shortcut way is to say we divide this negative 2 under there. Any way you want to look at it, when we divide by negative 2, you have to remember to reverse the less than sign. When you divide by a negative number, you reverse the less than sign. So when you reverse the less than sign, when you divide this side by the negative 2, you get x. The sign is reversed and it becomes greater than. And when you divide negative 4 by negative 2, you get 2. And so you're basically getting the same x equals 2 or more, but it's actually x greater than 2 because of that. All right? That's one way. That's if we group the x on the left side. Or as some people did it, they took the x over onto this side and they group it onto that side. They show that the answer will be the same. So starting back with the x minus 3 less than 3x minus 7. If I'm grouping the x values on this side, then this x will go over here, and this 7 will go over there. All right. So I would get, I'm grouping on this side, I would get 3x minus x on this side. Sign remains the same. This 7 goes over here and becomes positive 7. And I get positive 7, and then this minus 3 remains minus 3. So that here now, I'm having this same thing right here that I had before. And then what happens now? What happens next is that this side becomes 2x greater than, and this side becomes 4. And then I divide by the 2, divide by the 2. And I divide by the 2, this side becomes x. I'm divided by a positive 2, you know, so there's no need to reverse the sign. Don't reverse the sign because I'm divided by a positive 2. So I get x greater than 4, greater than 2. I divide by the 2, I get 2. Same as saying 2 less than x. So that is the same as saying x is greater than 2. So that's my answer. So whichever way you did it, your answer is supposed to be this, x greater than 2. All right, that's part 1. Part 2 now says we have to draw the number line for the solution. So draw the number line for this solution. So the critical value is 2, starting at 2. The inequality is starting at 2. So you draw a number line and number it up. 0, 1, 2, 3, 4, -1, -2. And that's enough. You can start here. The critical value is 2. So you put in a circle on the 2 to show that you start at 2. But I'm putting the circle, I'm leaving it unshaded. And some persons still shading when they're not supposed to shade. Leave the circle unshaded because there's no equal on the inequality. Mark it. This is not there. That equal part of it is not there. So because the equal part of it is not there, you leave this thing unshaded. Don't shade it. And you want greater than 2, so you put the arrow pointing to the right for greater than 2. But it's greater than 2. And you write the inequality on the line, x greater than 2, right there. All right, that's what it's supposed to have. Now, if this had the equal in it, it means that equal means that you also want the 2. So if you want the 2, that is when you would shade the circle. When you shade the circle, that is indicating that you also want the value of 2 and that you're starting at 2. All right. But as I said, the equal is not there. Right? The equal is not there, just greater than you want. And so that means that you don't want 2. You only want values greater than 2. And that is your number line for part 2. Part 3 now. Part 3 now is said if x is an integer. What's an integer? An integer right here is a positive or negative whole number. So it means that you're not taking values like 2.5 and 2.3 and 2.1 and 2. Anything. You're taking only the whole numbers, so like the 3, the 4, the 5, but that come next is 6 and so on. You're not taking the fraction parts. You're not taking the parts. You don't want like 2.7 and 2.9. That's what integers are, whole numbers. Positive and negative whole numbers. So if x is an integer, and if I were to write down a set of x values, then x integer x would have value. I could not include the 2 because it says greater than 2. And you indicate that by the open circle, the unshaded circle being on the 2. That means I'm not including 2. X is not equal to 2. X is greater than 2, but because it's an integer, you can't put like the 2.5 and the 2. Those values are not valid, right? Because the question said an integer, so you're starting at 3. The next integer will be 4, then 5, then 6, and these 3 little dots mean that you go on and on and on and on. So it's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to infinity. So those are the values of x. And clearly, then it means that the smallest one is this one. See there? That's the smallest x. So that is your smallest x value. That's what the question said. Smallest x value is 3. And that is your answer right here. All right, so that ends question 1. But good so far? But having a question
Yes,
before we
sir.
move on? But
No, sir.
all right, lovely.
Mm-hmm.
All right. All right. So those who made the mistake, I think one person last night actually shaded this thing. Was not supposed to be shaded. Hope you understand why now. All right. So you're gonna make the correction and take out the shading. In fact, 2 persons shaded it. But they sent me the solution so late, I could not communicate with them. It was too late. Right? Because I got it late last night. It was too late as I was preparing for this class today. All right, so good. So moving on now to question 2. So let's start question 2 on another page. All right, let's start question 2 here. All right, so question 2 now is our linear inequality. All right, linear programming. Now, as I said to you, they don't really set these questions this structured anymore. But if you can do these structured ones, the one that encompass everything from beginning to end, then you can do the little baby ones at the setting now. But guess what? Master these more structured ones first, so that the other ones become easy. All right? So, and remember, everything you do must make sense. So as you do the question, you're relating it to a real world situation. It doesn't make sense realistically. That's what you're looking at. Does it make sense realistically? And it comes to practice, understanding the terminologies and stuff. That's why I gave you that chart with the terminologies that I tend to use all the time. All right? So it comes with practice, guys. So that's why we have to practice. Okay. So question said, a shop stocks X phones and Y radios. Now, first thing I want to explain to you is that X is not phones and Y is not radios. X is the number of phones and Y is the number of radios. And we need to understand that. So X is a number, like 10 phones or 20 phones or whatever. Y is also a number, like 5 phones or 15 radios, 5 radios or 15 radios. X and Y are the number of phones and the number of radios. The thing is, you don't know how many phones and how many radios you're going to have in the store at any one time. You don't know. So what they do, they use X to represent the number of phones and they use Y to represent the number of radios. But you don't know what X is there, you don't know what Y is. And then what happens now is that you have all these conditions under which you can stop the phones and the radios. So these conditions now will determine how many phones you have and how many radios you have. And then now the conditions now will basically put you in a box. It's like put you in a restricted quantity of phones and radios that you can have to satisfy the conditions. That restricted quantity of phones and radios is represented by a common region where you represent the inequalities on a graph. So the points in the common region and also the points on the lines of that common region are the combination of the phones and the radios that you can stock to satisfy the conditions under which the store or the shop is going to operate to stock the phones and the radios. And they're basically saying them to you in words. And you're representing what they say in inequalities, and then you put those inequalities on a graph and get your region that shows where you can have the number of phones and the number of radios combination, various combination that you're allowed to have. All right. So the question says, the shop, it has shelf space for up to 20 devices. And almost everybody got that one right. Meaning you can only hold 20 devices. The shelf space that you have can hold only 20 devices. And the word devices is taken to mean the phones and the radios together, devices. So you have shelf space, you can only put 20. 20 is the maximum you can put on it. So therefore, the total number of phones and radios that you're going to have is going to be 20 or less than 20. You can't put more, right? So the first inequality, let's try it out first. So it says X phones and Y radios. Y radios. That's why you're stuck in X phones and Y radios. X is the number of phones, Y is the number of radios. First condition is that the shelf can only hold 20. That means the number of phones, which is X, plus the number of radios, which is Y, can't pass 20. Can be less than 20 or equal to 20. And that's the first inequality. First condition, the total of the phones and the radios can be 20 or less, because you only have shelf space can hold up to 20. Can't hold more than 20. All right? That's the first condition. Second condition starts with the start to tell us about the price. It says the owner of the shop spends $150 to purchase each phone. That's $150 for one phone. So if he's buying 2 phones, it's 150 times 2. If he's buying 3 phones, it's 150 times 3. If he's buying 5 phones, it's 155 times 5. He's buying X phones. So the amount of money spending on the phone is 150 times X. In addition to that, he's buying Y radios. We're spending $300 for each radio. See there? $300 for each radio. For each radio, for one radio, spending $300. So if he buys 2 radios, that is 300 times 2. If he buys 3 radios, that is 300 times 3. If he buys 4 radios, that is 300 times 4. But you don't know how many radios he's buying. The number of radios he's buying represented by Y. Right there. So therefore, the amount of money spending on the Y radios is 300 times Y. Simple as that. 300 times Y. So total that he spent, let me write the information up here first in terms of the value, so we can always have it. So in terms of the cost for the purchasing the phones and the radios, it is $150 each, meaning for one. And this one is $300 each, meaning for one. So therefore, the total he's spending on the phones is 150 times X, and the total he's spending on the radios is 300 times Y. Right? And the question says, she has $4,500 to spend. See here? She has $4,500 to spend on the purchasing of the devices. So the total that she's spending can't pass $4,500. The total that she's spending has to be $4,500 or less. She cannot spend more than that. All right. So how do you represent that now? How do you represent that now? The second inequality. So the second inequality, let's put it here, is that the total that she spends, which is 150 times X. And we do have to put the dollar sign, right? We do have to put the dollar sign. Plus the 300 times Y, the money spent on the radios, which is 300Y. That's the total money that she's spending on money on the phones plus the money on the radios. That total money can't be more than 4,500. It has to be less than or equal to the amount that she has, 4,500. So you see if I had a dollar sign here, dollar sign here, dollar sign here, it's almost like they cancel with each other. Like there are a unit and they cancel with each other. So you don't need to put them. All right, you're really getting an equation in X and Y. And you must realize that this can be divided through by 150. You must always simplify your equation, their inequalities down to lowest terms. So you can divide through by 150. All right, so when they divide through by 150, when I divide through by 150, I get X plus 2Y less than or equal to 30. So this becomes your inequality, the second inequality. X plus 2Y less than or equal to 30. So you're not going to work with this, you know. You're working with this one. All right, that's it. So that's the second inequality, really. The third condition is that the owner of the owner decides to stock at least, and this word at least is still messing up some persons. Just think of money, I tell you all the time. Think of money. At least 5 phones and at least 5 readers. Just think of money. If you must have at least $5, somebody say, how much for a sweet today? And the person say, you owe at least $5 for that, you know. That means there's $5 or more for it. So if you say at least 5 phones, it means 5 or more phones. At least 5 means 5 or more. So the number of phones, which is X, must be 5 or more. The number of radios, which is Y, must be 5 or more. So the man don't want to have a shop where he have less than 5 radios in night and less than 5 phones in night. It don't make no sense to have a shop if I'm going to have less than 5 phones and 5 radios. You want to make sure that this shop always have 5 or more phones in it and 5 or more radios in it. That's a condition that he's putting in for the shop. Right? So you read it, make it make sense to you. Right? And the days about a man stocking up a shop with phones and radios to sell. Right? So the number of phones, which is X, must be 5 or more. At least 5 means 5 or more. So it's greater than or equal to 5. That's what you write it. And the number of radios, which is Y. Because you want 2 inequalities next, you know. The other inequality is Y. Number of radios, which is Y, has to be same thing, at least 5, greater than or equal to 5. So those are your 2 additional inequalities. So you have 4 inequalities. So let me tell you something now. And there are certain things that you practice and know. If you have 4 inequalities, it means that you're going to draw 4 lines. And when you draw 4 lines, your shaded region is going to be between those 4 lines. Your shaded region is going to be between those 4 lines. So your shaded region is going to be a quadrilateral. And if it has 4 lines, it also will have 4 vertices. And therefore, the question asks you to write down the vertices, you know that is 4 vertices. So see the logics? 4 lines, 4 vertices. 4 inequalities, 4 lines, 4 vertices. All right, so these things you know. So you don't give me 3 vertices when it's 4 inequalities you have. All right, so we know we're going to have 4. So basically, those are your 4 inequalities. All right, 1 for the first part, 1 for the second part, and 2 for the third part. All right. So the next part now, let's turn now. The next part now, it says, they gave us this graph. So basically, they gave us that graph. I gave you a graph on the classroom, but I'm gonna do it from scratch. All right. But it says So on the graph is scaled 2 units to 5 devices. That's how I scale a graph, 2 units to 5 devices. All right, and it says draw the lines associated with the 4 inequalities, and then shade the region it satisfies all 4 inequalities, and then state the coordinates of the vertices of the shaded region. So remember, the vertices of the shaded region, especially important because that is where you go to find maximum and minimum anything you want to find, vertices. Part C says, so let me put down here. Let me put down here as a part B what we're going to do. All right, and we're going to turn to the graph and do it. So for part B1, I'm going to draw the graph, the lines. Part 2, I'm going to shade. I'm going to shade the shaded region. And part 3, I am going to do the vertices. I'm going to write down the vertices. All right, it's just that I need to show the graphs. I'm going to write these down, and then I'm going to do the graph next. All right, we're going to come to a part C. So I'm going to write the vertices under here. All right, we're going to come to a part C. I'm going to come to a part C. As you can put on the next page here. And part C tells us about the shop now, right? What he says, the owner of the shop sells the devices to make a profit, right? So he's telling us about the profit. $80 on each phone, meaning $80 on one phone, $100 on each radio, meaning $100 on one radio. All right, so let's put that information up here for the profit, right here. Let's put the profit information in blue. So in terms of the profit that he's making $80 each. $80 each on the phone. So if he says one phone, he's making a profit of 80 times 1. 2 phones is 80 times 2. 3 phones, 80 times 3. So if it's X phones, is 80 times X. That's the profit on the phones. He's making a profit of $100 on each radio. $100 on each radio. So if he says 2 radios, that's 100 times 2. 5 radios, that's 100 times 5. 10 radios, that's 100 times 10. So if it's Y radios, the profit he's making on the radios is 100 times Y. All right, so it's 80 times X for the profit on the phones, 100 times Y for the profit on the radios. Question says we have to write an expression for the total profit, not just the profit of anyone, the total profit. That's the profit on the phones plus the profit on the radios. Is the total profit. All right, so we're coming back down here now. We're going to write an expression for total profit. So for part 1, so for the purple. So for part 1, we're going to say total profit. Give it a reference. So we can reference it. Total profit. We're going to call it P dollars. And put the dollar sign there. We're going to call it P. Where the P is going to be the profit on the phones, which is 80 times X. Oh, don't put the dollar sign here, so already. So we know it's the P's in dollars. Plus 100 times Y. That will be his total profit. Profit from the phones plus profit from the radios. That's going to be his total profit. And the last part now says we have to calculate the maximum profit. So to calculate the maximum profit, we're going to have to test to see which vertex on the shaded region gives us the maximum profit. So we know we're going to have to do a test. I'm going to start it right here. I'm not going to do it yet, I'm just setting it up. So I'm going to have to test for maximum profit. I'm going to test which point gives me the maximum profit, which vertex. All right. I'm going to come off the graph now a little bit. Come off the PowerPoint a little bit, and I'm going to bring up the graph. We're going to do it. All right. All right. So let's go. So I'm going to go like this, go like that, go like that. I'm going to put this now here, and then I'm going to go for the graph. So I'm going to do the graph right here. All right. Remember the scale was what? 2 centimeters to 5. So I need to change these values down here. Let's change these down here. These axes values. Let's change them. So it's supposed to be 5 10, 15, 20, 35. I have to change these as well. All right. Change the scale. So it's gonna be 5, 10, 15, 20, 25, 25, 30, 35. All right, same thing up here. 2 centimeters to 5, 5, 10, 15, 20, 25, 30, 35. All right, so we're gonna draw a graph on that. All right, ready now. So going back for the lines now. So we're gonna draw. All right, so let's go now. I'm gonna write now the mean for each line that we're gonna represent on a graph. Right? Let's do that in blue. Or in red. Yeah, let's do it in red. All right. So we're gonna draw the graph for this one. First thing is, what does that line mean in terms of the graph? What does that inequality mean in terms of the graph? All right, what does it mean? The y over here is positive. When the y on the left hand side of the inequality is positive, less than means below. Less than means below. So we know that we're gonna go below a line. Below. And then now the line, the equal is a part of the inequality. The equal is a part of the inequality right there. So we're gonna draw a solid line, unbroken line. So I'm gonna draw a solid unbroken line. The line we're drawing is unbroken. And the line that we're drawing is x plus y equals 20. This is the same thing as with an equal sign. That's all. X plus y equals 20. That's one of the easy lines to draw. X plus y equals 20 line. It passes through 20, 0, and also passes through 0, 20. Easy line to draw. X plus y line. Crosses the y-axis at 20 and crosses the x-axis at 20. Let me write that a little bit better. Make sure you can see it. 20, 0, 20. So those are the 2 points on that line that we're gonna draw. But this one now, some persons still not getting this one so good. All right, pay attention now. Again, we're gonna have to draw that line, that inequality, and we're gonna draw the line associated with that inequality. All right. Now, first thing again, the y over here is positive, so the less than means below. So we're gonna go below that line, below. The equal is a part of this inequality. So it means that the line is a part of the inequality. So the line is gonna draw an unbroken. Unbroken. We're gonna draw an unbroken line. And the line that we're drawing is the same line associated with that inequality. Just replace this with the equal sign. The line associated with it, which is x plus 2y equals 30. So everybody pay attention once and for all now. How we draw this line quickly. The quick way to draw a line like this is to put down 2 points. Put down 2 points. One of them is going to make the x value 0. That's going to be a point on the y-axis, because on the y-axis x values are equals 0. The other one is going to make the y value equals 0. So you put on the y value there. And then you use the equation to work out the y value here. And you also use the same equation to work out the x value here. How you do it? Let me work it out for you. For this one, when the x is 0, let me work it out and show you. When the x is 0, this is going to become 0. So the equation is going to become 2y equals 30. So everybody can see it properly. The equation is going to become 2y equals 30 when the x is 0. And then to make y the subject, now you divide by the 2. So clearly, the y is going to be equal to 15. So right here, so the y value is 15. As simple as that, you know. Simple as that. And put this a little bit over more to the right. All right, so when x is 0, we're going to have 2y equals 30. And so the y is going to be 15. Then for this one now, you put in the x value, you put in the y value equals 0. So the y value equals 0 right there. So you're going to be left with x equals 30. Right? You're going to be left with x equals 30 when the y value is 0. So you put 30 right here. So x equals 30. And if you put in back these values in the equation, I'm add up to 30, you know. See, 0 plus 2 times 15 is 30. Right? So you get the point, you cannot even check it. I mean, that means if I make a mistake, suppose I make a mistake and write 15, 0, for example, instead of 0, 15. I can try it back in the equation, you know. Because if I put this equal 15 plus 2 times 0, 2 times the y value here, so 0. This only equal 15, you know, reach 38, so it means that the point will be wrong. So when you get your point, you can check it, don't just run, leave it. Check it back and make sure the point that you get is a valid point. But when you practice and so forth, you'll be able to look at it and know, right? You'll be able to look at it and know. But this thing is very easy, you know, but you just need to practice. So those are the 2 points, all right? Those are the 2 points. All right, I'm going to erase this now, you know. I'm going to erase this down here. All right, I don't need to do all of that to do it. Simple. For the first one, put 0 here, so 2y equals 30, so y equals 15 if you divide by the 2. Right? For the next point right here, so you put the y value equals 0. Because if y value equals 0, then 2y equals 0, you say the x equals 30. See there? X equals 30. Come on, I want everybody to get this part, man. Too much people struggling on that part. We can get 2 points quickly for your graph. All right? All right, let's do this now because I kind of run out of space. So for this one, it is unbroken again. It is above again, above. Unbroken because of the equal. So it's unbroken. And the line is x equals 5. X equals 5, which you know is a vertical line. X equals 5 is a vertical line. And then for this one, again, whatever is positive, so greater than means above. So this one again is above. Unbroken again because the equal is there. So it's unbroken again. And the line is y equals 5. And y equals 5 is a horizontal line. Remember those things. Because the x-axis is y equals 0. So y equals 5 is horizontal at the x-axis. So those are your lines, you know. I'm underline them in blue. The lines that you're drawing. So you're drawing this line, you're drawing that line, this line, and you're drawing that line. All right. So let's do them on the graph now over here. So I'm going to draw the lines with a different color. All right. Let's do them over here. All right. All right. Okay, good. So the first line is x plus y equals 20. So I need a line that passes through 20 here, so, and passes through 20 there, so. Simple as that, you know. I need a line drawing passing through those 2 points. Right? 20 and 20. So I'm going to put in a line. I'm going to put in a line on the graph. Diagonal line. I'm going to put 1 point at 20. I'll put the other point at 20. That will be a line. And I'm going to extend it. What must you always do? Must always label the line with the equal sign. So this line, I'm labeling this line X, labeling this line X plus Y equals 20. Label the line with the equal sign. So some persons put in the inequality on the line. No. Label the line with the equal sign. The line is the equal mark. And you put an arrow pointing down. That means you want below the line. So the reason that you want is somewhere under here. We're not finished yet. You have to put in all the inequalities first. But you know that you're going below that line. But don't shade anything yet. Know that you're going below that line. The next one is this one. The next line is this one right here. All right. But what you do, I have 2 points that you're going to use. That means you put them down properly. This one is on the y-axis. This one is on the x-axis. So 0, 15 is right here. Guys. 0, 15 is right here, and 30, 0 is right here. So you need a line passing through those 2 points. All right, you need a line passing through those 2 points. So I'm going to put in a line again. Again, I'm going to put 1 point up here at 0, 15, right there. And the other point, I'm going to put it down at 30, 0, right there. I'm going to stretch it out, extend that line. That line is x plus 2y equals 30. So I'm going to write it here. X, position. That's it. I'm going to label the line now. X plus 2y equals 30. Always label the line with the equals sign. X plus 2y equals 30. So that is the line. So right away now, going below this line as well. The arrow pointing down. So the region that we want is somewhere under here. We'll make the 2 lines. We're not finished yet. Don't shade anything yet. We're narrowing in on the region that we want. All right. So this is a vertex right away now where the 2 lines meeting. All right. Some persons ignore that vertex for some reason. The next line now is x equals 5. And going above. Above a vertical line means that we're going to the right of the vertical line. X equals 5. So the x equals 5 line is going to be a line up here. Let's draw it properly. Let's put in a vertical line. I'll put it right here. X equals 5 is a vertical line passing through 5. I'm going to extend that up. Label the line with the equal signs. I'm going to write x equals 5 on the line. Put the arrow pointing to the right, means above. Above a vertical line is to the right. So the region that we want is somewhere inside here. But again, we're not finished yet. We have 1 more line to put in. All right. Next line we're putting in now is y equals 5. Y equals 5 is a horizontal line passing through 5. So it will basically go like this. All right. So let's put it in with the graph horizontal line. I'm putting it here. Y equals 5. And draw the line. So extend that line. All right, so remove that labeling that I had, put it further down. All right, so I'm gonna label this line. Let's extend this again. And label it y equals 5. I'm going above this line. So I'm gonna label this one down here. This line right here is the line x plus 2y equals 30. All right, leave it to the equal sign. So my region that I want, let me shade it in a different color now. Let me use this blue to shade it. Let's shade it blue. The region that I want is right inside here. That's my shaded region. This region satisfies all the inequalities. That region there. That's a shaded region. All right, so let me zoom it up now. That's a shaded region right here, guys. Satisfies all inequalities. All right, and because it's bounded by 4 lines, it has 4 vertices. All right, so shade, we've done this now, you know. See there. Finish this. We draw the graph. We draw the graph. Shade the region. Next, we need to write down the vertices. So let's name the vertices over here. Let's name them. Let's use let's use a different color. Let's use that and see if it will show. All right, let's use that. See if it will show. Right. So this is one vertex right here, which you can call A. It's another vertex right here, which you can call B. It's another vertex right here, which you can call C. It's another vertex right here, which you can call D. I'm gonna write them down over here, coordinates. All right. On the graph. Clearly A is a 0.55. So A is a 0.55. Then B. B is 12.5. Halfway between 10 and 15 is 12.5. I'm going to tell you something about B just now. So it's 5, 12.5. And then C is 10, 10. C is the point 10, 10. And then D is a point 15, 5, 15, 5. So those are your vertices. Now let's talk about point B a little bit. Point B. Let's talk about point B a little bit before we move on. Point B. Remember I told you that when a vertex cannot be used, you go along the side. I told you that. Told you that one day. Now remember, you can't sell 12.5 radius, you know. That is saying 5 phones and 12.5 radius. You cannot sell 12.5 radius. So you would have to work with a value 5 and 12. You can't go 13, because if you go 13, you're coming up here outside the region. Right? So you can't use 13, because 13 would take you up here. Right? You have to go along the side. So because you can't use 12.5 radius, you really have to use 512 for the point B. I didn't really stress purses over it, but it's really 512 you have to use for the point B. So when you can't use a vertex, when you can't use a vertex, as in this case, because of 12.5, you cannot sell 12.5 phones, you really have to go along the side. And the value would have to be 12. You can't sell 12.5. You can't use 13, because 13 will be taking you above and outside the region. Right? Outside the region. But understand that? But understand that concept?
Yes, sir.
Yes, sir. All right. Just that when you use the 12.5 in your calculation, it came out not to be the maximum anyway, and so there was no need to worry. All right. So anyway, so we're gonna test for the maximum profit down here now. Test for the maximum profit. All right. So we're using the vertices. I'll drop in the coordinates of the vertices in the formula for the profit. All right. So test for maximum profit. The profit at A, using the coordinates of A. No, we're not doing A out of it. All right. So this is so A out of it, we don't need to test A. A clearly out of it. So don't waste time and test A. But what happened with this classwork is that plenty of people ignored the point C. Don't know why, but plenty of persons ignore the point C. C is a vertex as well. And you have to include C. Why we have to include C? Let's reason it out again. Remember that this one has a higher Y value than all of them. But this one has a higher X value than B. And it has a higher Y value than D. But D now has the highest X value, right? But it has a lower Y value than C. So you have to test all three, A, B, and C. You have to test all three of them, right? Plenty of people left out the C, so I hope you learn from that mistake, all right? You cannot eliminate it like that. Only the one that you're certain about is A. A clearly not going to be the maximum, all right? So we're going to start at B. So for B, I'm going to go 80 times 5 plus 100 times 12. You can't sell 12.5 radius. Hope you understand that. You could not use 12.5. You cannot sell 12.5 radius. Right? So you really should be using 12. All right? So it's 80 times 5 and 100 times 12. So that is 1600. So the profit at B really is 1600. You can't sell 12.5 radius. You can only sell 12 radius. All right, over to C. Profit at C will be 10, 10. 10 phones, so it's 80 times 10 plus 100 times 10 again, because it's 10 radius. And that is 1800. And then the profit at D, where you're selling 15 radius, is 80 times 15, phones, 15 phones plus 5 radius, 100 times 5. That's what you're doing there. All right. That's 1700. So clearly, that's your maximum profit. And you have to write a conclusion. Your conclusion. You cannot just leave it there. And you don't say your maximum profit is C. No, C is not can be a profit. The profit is the money value, the $1,800 you make. You can't say the profit is a point. You can say the maximum profit occurs at point C, where we have 10 phones and 10 radios. Be explicit, be specific, be exact. That is how mathematics is. Has to be precise and exact. So spell out everything. Leave nothing ambiguous. Because if it's ambiguous, depending on who mark in the paper, you might get the marks or not get the marks. Make it clear as day. It's easy with mathematics to make things clear. Because mathematics is the most exact science. All right, so you're going to spell it out. Maximum profit is, and you put the dollar sign in front of it now because it's money. $1,800 when, telling the condition, 10 phones and 10 radios are sold. And that was a question. That's the answer. Last part. All right. So those who did not get it right, those who did not do it smoothly, I need to go and redo the question. Everybody. All right. Those of you who did not do a good job at it, you need to go and do it again. You don't. Well, you know when you don't do a good job at it. When you have to be looking back over stuff, making mistakes, doing this, doing that, up and down, you don't do it straight, fluent from beginning to end. That's why I want you to do your questions. Just flow from beginning to end without stopping and checking this and erasing this and making a mistake here and there. No, I don't want that. I want the body to just be able to work the question straight. CXC exam don't afford time for you to be erasing and correcting and checking over one thing, right? It's like 10, 15, 12, 10, 12, 15 minutes of work. You have to do a question, This question would have to be completed in 15 minutes, Usually it takes longer because I'm explaining as I go. If I were to do this question straight, you can finish it in 10 minutes or less. Right? When you know your stuff and you can just do it straight. Right? And that's how quickly I want you to be able to do it. All right. And you can only do that when you know your stuff inside out. And you can know your stuff inside out by practicing. All right. So everybody go there so far? I'm moving on to our next topic now. So for the next topic, I'm gonna do half of it today, some of it today, and I'm gonna do the rest of it tomorrow. It's a 1 week topic, the matrices, and then we're gonna go into transformation. We're gonna do the full transformation, which also applies matrices. All right. So that is the plan for next week. But before we can go to transformation, we have to know matrices. All right. We're not gonna just do the baby matrices. We're gonna do the calculation with the matrices. Transformation. We're not gonna do this baby transformation. We're gonna go to the calculations transformation. We're using a lot of matrices. So you have to do the matrices topic before. All right. So that is why we have to do this. All right. So let's prepare this now. Okay. All right. So I just want us to get to a certain point with the matrices today, and then we'll finish it off tomorrow. All right. So let's do a good bit of it today. So far we can reach today. See if we can get up to multiplication of matrices today. And then tomorrow we'll take it forward using matrices to solve equations. All right. That's the extent. And then I can show you some nice things about matrices never applied. So remember, we're doing this topic today, tomorrow, and Wednesday we'll have a classwork on matrices. All right. All right. So let's go. So what are matrices? So matrices are used to arrange large amounts of data in an ordered form, an ordered and manageable form. So it's like a table, like how you do the table. I mean, in the workplace, for example, when they have a lot of data to manage, they tend to put them in tables. But they can also put them as matrices. right? It's just that persons who are now using those matrices would have to understand the content of the matrix, right? When people have certain information that they want to put data in and hide the data, they don't want persons to know what the data is representing. They just put them in matrix, and only certain persons now would know what the columns in the matrix are, what the rows in the matrix are, right? So that is it. You can use it to represent a large number of data. And then the data now is arranged, it is put in an arrangement consisting of rows and columns. All right, so the data is arranged in this forms an array for number of numbers, forms an array of numbers or data. It don't have to be numbers, it can be anything consisting of rows and columns, just like a table. All right. So as an example, let's take a simple example here. In a football competition, I'm just using 3 teams. Now, normally in real life, you might have 15 teams, 20 teams in a competition. All right. And you want to show the results for the games won, games drawn, games lost. You might also want to put in the points against, goals for, goals against, and all these things in the real world. So a lot of data you can put in. Games remaining, average goals per game, and all these things that you might want to put in. But I'm just simplifying it to 3 teams and 3 things: games won, drawn, and lost. You might put the information in a table like that. But instead of putting it in a table, you could also put it in a matrix like that. And then the organizers of the competition would know that the rows are for the teams. The rows are for the teams. Right? They would know that these are for the teams. So that's Team A, Team B, and Team C. And then these now are for the games won, games drawn, and games lost. So the organizer of the competition could look at this matrix here and know exactly what it is saying without having to put these things up here and these things down here. That's a simple example of what a matrix can be used for. In a store, for example, a matrix can be used to show the price of goods. So let's say you have 3 items. They're selling phones of 3 types, right? So you have phone 1, phone 2, phone 3. You can put a matrix. You put the price of the phones in there. So you put $100, $120, $130, or $125. And those will be the price of the phones. And then you might have another matrix. You put the quantity of phones sold. You might have 20 of this phone sold, 22 of this one, and 30 of this one. And you know that this one is for the number of phones sold, and this one will be the price of the phones sold. And then you can use these 2 matrices to work out the total money that you get from the sale of phones. All right, we're going to see examples like that later on. All right, but those are examples of matrices. Right? That's basically what matrices are. Let's go into the types of matrices now, or more information about matrix in terms of order and these things. All right, so order or size of matrix. What do they mean by the order or the size of a matrix? So a matrix is expressed in a form that gives the number of rows by the number of columns. The number of rows by the number of columns is called the order or the size of the matrix. The order or the size of the matrix. So the word order and the word size in relation to matrix are 2 words that are used interchangeably. So you might say a question that says the order of a matrix is something, something. Another question might say the size of a matrix is something, something. Order and size mean the same thing, right? We're talking about the number of rows by the number of columns. So the order is basically a way of telling you how many rows the matrix has and how many columns it has, right? So for example, that is it. So the order is rows by columns. So sometimes they'll put times here, but it don't really mean multiply. It really means the word by. So when they put the multiplying symbol in there, it really means the word by. So it's basically how many rows it has and how many columns it has. Always state the rows first. Always state the rows first. All right. And so the rows now are the horizontal data in the horizontal, and the columns are the vertical data in the vertical. All right. So this example, as an example, this example has 3 rows and it has 4 columns because it has 3 sets of data across and 4 sets of data down. All right. So your rows would be R1. So R1 would be 6211, and R1 is the notation used for row 1 actually. R1 is the notation used for row 1. R2 is used for row 2. R3 is used for row 3, and so on. All right. So that would be a row 1. And that would be a row 2. 3, 2, 2, 1 would be row 2. So row 2 would be 3, 2, 2, 1. That would be row 2. All right. And then row 3 would be 3, 1, 1, 0. And then the columns now are your vertical data. And there are 4 columns. And columns now are C1, C2, C3. So R is for rows and C is for columns. So the first column is called C1. That is 633. 633 is column 1. This one right here. 633 is your column 1. C1 is your column 1. All right. Then C2 is 221. C3 is 121. C4 is 110. And because it has 3 rows and 4 columns, then we say that this is a 3 by 4 matrix. It is a 3 by 4 matrix. 3 by 4 matrix. Times here don't mean that you're multiplying anything. This don't mean that you're multiplying anything. It's just a way of saying what the size of the matrix is, or what the order of the matrix is. So it's a 3 by 4 matrix. Other examples that has 2 rows, 2 columns, and this is one of the size matrix. One of the size that we're going to be seeing a lot. We're going to see that one a lot. Most of the questions will consist of 2 by 2 matrices. That's a 2 by 2 matrix right there. All right, see there, that's a 2 by 2 matrix. And that one is a 2 by 3 matrix because it has 2 rows and 3 columns. 2 rows and 3 columns. So that will be a 2 by 3 matrix. But understand that so far? Before we move on, that is just the size or the order of the matrix. R is used to represent the rows. C is used to represent the columns. So it's R1, R2, R3 for the rows. C1, C2, C3, C4, and so on for the columns. But good so far. Before we move on.
Yes,
Understand the basics.
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Everything important. All right. Types of matrices now. And I want you to pay particular attention to these. And today is one of the things you want to do is revise these things. Types of matrices. All right. A row matrix. A row matrix is a matrix that has 1 row only. A row matrix. And that matrix over there is an example of a row matrix. It has only 1 row. It has 2 columns, but it has only 1 row. That's an example of a row matrix. All right. So naturally, a column matrix is one that has 1 column only. And we're going to be using a lot of column matrices. We're going to be using a lot of these in our work. We're going to be using a lot of it in transformation. And I'm going to be using a lot of it in matrices. I'm going to be using a lot of it in vectors, column matrices. All right, so we're going to be selling a lot of those. That's a column matrix. It has 1 column only. This one has 2 rows, but even if it had 3 rows, even if it had another value here, like maybe 6, and this was like that, it would still be a column matrix. All right, so it's a matrix with 1 column only. A null matrix or the 0 matrix is a matrix 0, 0, 0. All the values equal 0. I've never seen a question with a 0 matrix in it, but still it's on the syllabus. Something to know. I've never seen a question in CXC where they give you a 0 matrix to do anything. Because 0 matrix behaves just like the number 0. The value is 0. Behaves just like the regular 0 in maths. All right. So that's what this is saying. The null matrix or the 0 matrix behaves similar to the number 0. In that, for example, 0 times anything is 0. And anything times 0 is still 0. So when it comes to multiplying, if you multiply the 0 matrix by another matrix, you're going to get back the 0 matrix. But that's, I've never seen any question done with it. All right. So it behaves just like the number 0 in regular maths. This 0 null matrix. And the symbol for the 0 matrix is Z. Z. All right. Moving along. A square matrix. A square matrix is any matrix that has the same number of rows and the same number of columns. And there are certain special things that you can do with square matrices that you can't do with other matrices. All right. But they're not going to test those things. But this is a square matrix. These are examples of square matrix. And the square matrix that we'll mostly see, as I said, is a 2 by 2 matrix. So a square matrix is a matrix that has the same number of rows as there are columns. So like a 4 by 4 is still a square matrix. All right. Most of the square matrices that we're going to see, most time we're going to be seeing square 2 by 2 square matrices in our questions. All right. Then a diagonal matrix. What's a diagonal matrix? A diagonal matrix, first, it is a square matrix. A diagonal matrix is a square matrix where only the elements on the main diagonal are not equal to 0. What do we mean by the main diagonal? The main diagonal is a diagonal that runs from upper left to lower right. Let's put it on a diagram. That's the main diagonal. Now, sometimes they call it primary diagonal, leading diagonal, first diagonal. Any word that means first can be used to describe that diagonal there. All right? So in this diagram, the main diagonal will be the elements down here, or the leading diagonal, or the first diagonal. So depending on which teacher teach you, teacher might call it first diagonal. Another teacher might call it primary diagonal. Another teacher might call it leading diagonal. Any word that means the same as main or first can be used to describe that diagonal. And so a diagonal matrix is one where only the elements on the first or leading or main diagonal not equal to 0. So if I draw another example, a 3 by 3, remember it has to be a square matrix, you know. I put a 3 by 3 and I put 5, 9, 2 down here, and then all the other values equals 0. And that is a diagonal matrix, a diagonal 3 by 3 matrix, because only the elements on the main diagonal or the leading diagonal not equal to 0, or the first diagonal. All right. The other diagonal over here, they call it the second diagonal, or the secondary diagonal, or the following diagonal. Any word that means second can be used to describe this diagonal. Any word that means first can be used to describe that diagonal. All right. So I don't want you to stick to main. All right. So if it's a leading diagonal, they're talking about the same thing. Following leading diagonal, first diagonal, primary diagonal, main diagonal. It's talking about that diagonal. The other one is trailing diagonal, following diagonal, secondary diagonal, second diagonal. Those kind of words are used to describe this one, the second diagonal. All right, good. Let's move on. The next word I want to, so that's it. The main diagonal of a square matrix runs from upper left to lower right. The next matrix we're going to be seeing a lot of in this exam, you have to know and understand is the I matrix or the unit matrix. I want to put a note on it, note of it. It is the identity matrix for multiplication. Right? So this is really the identity matrix for multiplication of matrices. So put a note on that for me, please, or make a note. This is for multiplication of matrices. Multiplication. Because the zero matrix is the identity matrix for addition. And this is the identity matrix for multiplication of matrices. For multiplication of matrices. The identity matrix. What does that mean? It behaves just like the number 1. In that any number you multiply by 1 and give about the same number is the same thing with this identity matrix. Any matrix you multiply with the identity matrix, you are getting back that same matrix. Right? So it is the identity matrix of multiplication. We're going to do some additional stuff later with the identity matrix. But I want you to get familiar with it from now. And sometimes in an exam question, they'll just give it the letter I. And you have to know that the I is actually equal to this. You have to know. So some questions, they just give it the letter I, and you have to know that it is this. Note clearly 1, 1 on the leading diagonal, and then 0, 0. Look at the values carefully, everything important. So if you put this, that is not I. This is not I. This matrix is not the I matrix. That's a different matrix. All right. So don't mix them up. We're going to see this matrix or the transformation. All right. We're going to see that matrix or the transformation. All right. So that is the I matrix or the identity matrix or the unit matrix. It's the identity matrix for multiplying matrices. All right. So the identity matrix, as we said, behaves just like the number 1. So as we are basically saying, 1 times a number equals the same number, same thing. I times a matrix equals the same matrix. A matrix times I equals the same matrix. A matrix times I equals the same matrix. This I matrix is similar to the number 1. It behaves just like the number 1 in regular numbers. All right, think of it that way. All right. Then we come to the singular matrix. Another thing that we're gonna see a lot of questions about the singular matrix, and we're gonna spend some time dealing with singular matrix by itself. Oh, what did I get? I made a mistake. Stop sharing. All right, body back with me. Made a mistake and press the stop. Body back with me. All right, good. Right, so back to the singular matrix now. As I was saying, the singular matrix, we're gonna spend some time dealing specifically with the singular matrix because it's a very important matrix in the sense that a lot of questions are set with singular matrix. So we're gonna spend some time specifically dealing with singular matrix. Maybe we're gonna get to it tomorrow. Based on where we are. All right, we're actually get to singular matrix tomorrow. So you have to know everything about singular matrix. So we're gonna spend some time emphasizing the nuances and the minute details about singular matrix, the definition, why the matrix singular, and all these things. All right, but for now, let's know that a singular matrix is one that has no inverse because the determinant equals 0. So there are 3 things that mean with a singular matrix. 3 things. Singular has no inverse, determinant equals 0. Those are the 3 things that are associated with a singular matrix. So a question might tell you that a matrix in a matrix, yeah.
What do you mean by determinant?
We're gonna get to it. That's why I tell you I'm not gonna go into too much details right now. We're gonna get to it eventually. All right. So maybe I shouldn't even bother to start talking about it. I have to learn about determinant before we can understand singular matrix. So let me just stop it there. When we get to it, we'll emphasize all these things. All right. So I'm going to teach you about what determinant is later. It's just one of those components that they use in matrices to find inverse. All right, so let's leave it at there for now. So we're going to deal with the singular matrix by itself later on, but it is very important for us to know and understand it. But don't worry about it yet. Don't worry about it. We want to deal with it by itself. All right, so let's stop it there. All right, let's continue. Let's start with some operations now, some real operations. And the most basic of operation that you can do with matrices is to add and subtract matrices. So we're getting into the calculation part now. That first part was just for us to introduce some terminologies that are used in matrices. Now we're going to do some actual operations. So add and subtract. Now the first thing is that 2 matrices can only be added or subtracted if they are the same size or the same order. So you can't add 2 matrices that are not of the same size. You can't subtract 2 matrices that are not of the same size. That's the first thing. So matrices can only be added or subtracted if they are of the same size or order. All right. And what you do, you add or subtract the corresponding values or the corresponding elements of the matrices. That's what you do. To add 2 matrices, we add together corresponding elements of the 2 matrices. Simple, straightforward, almost common sense. We can go straight into an example. So once I add those 2 matrices, they are of the same order, same size. So what it is that these 2 elements are corresponding elements. So we add them together to get that one. But you can understand that. But that makes sense?
Yes, sir.
Yes, sir.
So add those 2.
Yes,
We'll add those 2, we're gonna get 7 right there. Simple as that. And then these 2 are corresponding elements. So you have to add them to get the element going there, which is 5 and 7 is 12. So you get 12 right there. And then the element for here is obtained by adding these 2 that are corresponding elements. That's 9 and 6, that's 15. So get that element, you add them, you're gonna get 15. And then for the element here, you add these 2 to our corresponding elements. That's 1 and 5 is 6. 1 and 5 is 6. So that is 6. Simple. Don't even spend any more time on that. Can just move on. Same thing for subtraction. Same thing for subtraction. Subtract the corresponding elements. So now we're subtracting the same two matrices. Same thing again. And you do it algebraically, meaning you take the sign, positive and negative sign, and so forth into consideration. All right. So the element for here is obtained by doing this one minus this one, which is 4 minus 3. 4 minus 3 is 1. So that value there is 1. And then for this value here, it is 5 minus 7. 5 minus 7 is negative 2. 5 minus 7 is negative 2. What did I do? Did I stop it again?
Yes,
Dad.
Okay. Oh Lord, hold on. All right. Let's get back to it. Right. So back to this again. So 5 minus 7 is negative 2, as we said. Right? So 5 minus 7 is negative 2. And then clearly it's 9 minus 6, right? It is 3. And 1 minus 5 is negative 4. About to go to that? So
Yes,
that's
sir.
easy.
Yes,
Subtraction
Dad.
of matrices, they have the same size. You add or subtract the corresponding values. So let's move on. Addition and subtraction. Then we come to multiplication of matrices now, which is a thing in itself. Multiplication of matrices. Now you can multiply a matrix by a value, which is called a scalar, or you can multiply a matrix by another matrix. And to multiply a matrix by another matrix, there are certain conditions that must be in place first. And 6, you like to test your knowledge on these background information or these conditions that must exist for you to be able to multiply matrices. So when I get to that part, I wanted to pay particular attention to the conditions under which two matrices can be multiplied, right? And when they are not able to be multiplied, and also pay attention to what the resulting matrix will be. But first, say multiplying by another scalar value. Multiplying by a scalar value is the first thing, right? Which is multiplying by another number. You just basically multiply each value in the matrix by that number, right? Right? In this case, each element of the matrix is multiplied by the number. Simple and straightforward. So if I multiply that matrix by 3, I multiply 3 times that matrix, then I multiply each of the elements in the matrix by 3. Each element is multiplied by 3. So 3 times the 2 is 6. 3 times the negative 1 is negative 3. 3 times the 6, 3 6 are 18. And 3 times the 4, 3 times 4 is 12. But good?
Yes, sir.
Simple and straightforward. Good. So when you multiply a matrix by a number, you multiply each value by the number. All right? Whether that number outside is a fraction or a whole number or even a variable like a letter. So if for example, it was x times 2 minus 1, 6, 4, then clearly this will become 2x minus x, 6x, 4x. That's what you will get. Those will be the 4 elements. All right, you multiply each value by the constant or by the value outside. All right, so let's move on now. Multiplying by another matrix. So we're going to go straight into the conditions now. And then we're also going to look at how the procedure is carried out. But let's deal with the conditions first. And I want you to pay particular attention to this. CXC is testing your knowledge of this thing a lot. A lot of exam papers these days, you are testing your knowledge if you know the conditions under which two matrices can be multiplied. So make sure you get this. If you don't understand it, ask me, let me explain it. All right, so let's go. The rule is two matrices can be multiplied only, two matrices can only be multiplied together if, can only multiply two matrices if the number of columns in the first matrix is equal to the number of rows in the second matrix. So like I'm multiplying two matrices, in order for the multiplication to be possible, the number of columns, note the number of columns in the first matrix must be equal to the number of rows that is in the second matrix. The number of columns in the first matrix must be equal to the number of rows of the second matrix when you're multiplying two matrices. All right. So that is an example right here. So if I have a 4 by 3 matrix and I'm multiplying a 3 by 2 matrix, then this multiplication is possible. Why? Because the number of columns in this first matrix is 3, and the number of rows in the second matrix is also 3. Remember, I know it's always rows by columns. Rows by columns. So this matrix has 4 rows, 3 columns. And this matrix has 3 rows, 2 columns. The multiplication is possible. The multiplication is possible because the number of columns in the first matrix and the number of rows in the second matrix match. They are equal. All right? So that's what we're going to say. Pay attention to the details, guys. So those two are equal, so the multiplication is possible. And after the multiplication is possible, the resulting matrix will have the same number of rows as there are in the first column and the same number of columns as there are in the second column. So the resulting matrix is going to be a 4 by 2. Pay attention to the details, everything important. See there? The first matrix has 4 rows, so the resulting matrix will have 4 rows. The second matrix has 2 columns, so the resulting matrix will have 2 columns. Everybody understand that?
Yes, sir.
Yes, sir.
Make it stick, ladies and gentlemen. Let it stick for the multiplication to be
Repeat, please,
possible.
sir.
Huh?
Can you repeat, please, sir?
Let me repeat it again. All right. For 2 matrices, for the multiplication of 2 matrices to be possible, the number of columns in the first matrix must be equal to the number of rows in the second matrix. If that is not the case, then the multiplication is not possible. The number of columns in the first matrix must be equal to the number of rows in the second matrix for the multiplication to be possible. All right, so giving an example now. So let's say I have a 4 by 3 matrix. What do I mean by a 4 by 3 matrix? Let's put it over here. So let me put it over here. So like I'm multiplying 4 rows by 3 columns. So look, I'm doing this. Look over here. 4 rows. 1, 2, 3, 4. 4 rows, 3 columns. 1, 2, 3, 1, 2, 3, 1, 2, 3. See that? That's a 4 by 3 matrix. And I'm multiplying that by another matrix. So I don't have to put the multiplication sign. I'm multiplying that by another matrix that has 3 rows and 2 columns. 3 rows and only 2 columns. So I'm multiplying those 2 matrices. Now these little dots are values, you know. I'm just showing you the position. So I have these 2 matrices multiplying together. But understand that this one is a 4 by 3. That one. And this one is a 3 by 2. Understand that? I'm representing what I have over here now with this up here. So good? So far, so good?
Yes, sir.
Yes,
When I
sir.
multiply these two, it is possible to multiply them because the number of columns in this matrix and number of rows in that matrix equal 3. They match. They match. Right? The number of columns where this one have is 3. And the number of rows where this one have is also 3. So because the number of columns in the first matrix match the number of rows in the second matrix, the multiplication is possible. Right? This has 3 columns and this has 3 rows. So the multiplication is possible. And what will be my resulting size? The resulting size of my final matrix is going to be what? My final matrix is going to have a size. My resulting matrix is going to have a size such that it has the same number of rows of the first matrix, which is 4, by the same number of columns of my second matrix, which is 2. So my resulting matrix is a 4 by 2 matrix. 4 rows and only 2 columns. That's gonna be my resulting matrix. Those are the position that my resulting matrix will have. See, 4 rows, 1, 2, 3, 4, 2 columns, 1, 2, 2 columns, 1, 2. My resulting matrix will have 4 rows and 2 columns. So you know what to set up when you're doing. Everybody good so far?
Yes, sir. Yes, sir.
Yes, sir.
All right. So let me put it back over here now. Bam. Those two match. The number of columns in this first matrix and the number of rows in the second matrix, they match. 3 columns in the first matrix, 3 rows in the second matrix. So yes, the multiplication is possible. The resulting matrix will have the same number of rows as there are in the first matrix, and will have the same number of columns as there are in the second matrix. So my resulting matrix is going to be a 4 by 2 matrix. And then all that will let me know is that there's a way to use these rows and these columns to calculate the values inside here, which we're going to look at next. All right. I'm going to show you what you multiply by what value you multiply by what value to get there. But that's the first thing I want us to understand. So, better go to that so far.
Excuse me,
Better go
Dad.
to that so far. Yes.
What do you do? What do you do if the column and the row aren't the same? You
You
just
just
can't
can't
multiply
multiply
it
them.
altogether.
Can't multiply. There's no result. Not possible. That's right. Not possible. Not
Okay.
possible. All right. Not possible. Not possible. So, for example, if I switch these two around, let's just switch them around, and I'm trying to do the 3 by 2 times the 4 by 3. So this matrix would have 3 rows and 2 columns. And I'm trying to multiply that by 1, 2, 3, 4, and 3 columns. 1, and that's the third column. I'm trying to multiply these two. Not possible. Not possible. I can't get any result. It's not possible to multiply them. Why? Because these don't match. These don't match. Number of columns and the number of rows here not equal and not equal. Therefore, not possible.
So we'll
Multiplication is
still
not
get the
possible.
marks on the exam if we put not possible.
But that will be the answer. Not possible. That is the answer.
Sir,
You know, you
what
can't do it.
isn't
You
by
can't
3?
work out something that cannot be worked out.
Sir,
Let me
isn't
tell
4
you.
by 3 greater than 4 by 2?
Huh?
Isn't
Those
4
that
by 3
listen.
greater than 4 by 2?
Listen, I never talk not about no size, you know, boss. Size of the matrix, you know. I never say anything about the size that determines whether it can or not, you know. I said the number of columns in the first matrix and the number of rows in the second matrix have to be equal for the multiplication to be possible. Irrelevant of what this is. It don't matter what this value is. It don't matter what this is. It don't matter what that is. If you put 10 here, so, if you put 10 here, so, then this is going to be 10. If you put 50 here, so, then this is going to be 50. See that?
Yes,
You
sir.
understand that? Good. Them two things they look upon. The columns in the first matrix and the rows in the second matrix have to be equal, regardless of what they are, the size of the matrix. No matter how big the matrix is, how small the matrix is. That is irrelevant. All you need to know is that the number of columns in the first matrix and the number of rows in the second matrix is the same. That's all you need to know for the multiplication to be possible. Then once it is possible, that no is when you go to this. That no is when you go to this. When it is possible, then number of rows come here, so in the final matrix, and number of columns come there, so regardless of what it is. So if this was 6, then this would have been 6. If this was 9, then this would have been 9. Want to switch them around? I can switch them around. Switch them around. If this was 9, then this would have been 9. And if this was 6, then this would be 6. You see, say no matter the size, which one bigger than which? You see that?
Yes, sir.
All you need is for these and this to be equal. If them not equal, then you're not answer. You're not answer them two that are equal. So as I did here, right? I made them not equal. I put 2 under 1 and put 4 there. So 2 columns that one I have, 4 rows that one. You can't multiply them. Cannot be multiplied. Even though the number of rows just and the number of columns just are the same, it no matter. Can't multiply. Once them two number they not the same. In terms of the number of columns and the number of rows. Remember the 2 is a number of columns. And the 4 is a number of rows. It's not a value of 2 and a value of 4. No. 2 represent the number of columns and 4 represent the number of rows. The 2 is talking about this. 2 rows. And the 4 is talking about this. 4 columns. No, two columns, sorry. 2 columns, 4 rows. They don't match. So you can't multiply these 2 matrices. Cannot multiply them. Cannot multiply them. It's not possible to multiply them. Multiplication of matrices is a special thing. They can only be multiplied under certain conditions, and these are the conditions. And CXC is going to test you on it. CXC will test your knowledge of these conditions. What they do sometimes, they give you 2 matrices to multiply. Here example. They give you 2 matrices to multiply, right? One of the matrices is represent money, and the other matrices represent one matrices represent price in money, price of something. And the other matrix represent the number of items sold, number sold. Now remember, suppose you sell something for $100 and you sell 5 of them. Normally in maths, you can multiply the 100 times 5 and it's 500. Or you can multiply the 5 times 100 and it's still 500. With matrices, depending on the size of these 2 matrices, you can either multiply them this, you can either multiply them this one times a 1 here, or maybe you can't do it that way there. So you have to do it this one times that 1 here. You have to set them so that the multiplication is possible. I'm going to see that question. I remember that particular question. We're going to see it one of these days. Right? The multiplication has to be done such that the number of columns in the first matrix match the number of rows in the second matrix. I think I spent enough time on that. I've been saying the same thing over and over again. You must get it by now. All right? So I can continue. So how do we do the multiplication now? That's the next thing now. So now that we know if the multiplication possible or not, when the multiplication is actually possible, how do we do it? How do we do it? Look how we do it now. We multiply the rows of the first matrix by the columns of the second matrix. We multiply the rows of the first matrix by the columns of the second matrix. And you multiply the values along the row and down the column. I'm going to show you. So all of these statements don't make no sense. Sometimes the best way to demonstrate what I've said is to actually do it, demonstrate it. And for you to understand what I've said is for me to do it. So I want to do an example. But remember, you use the rows of the first matrix and you multiply the columns of the second matrix. You multiply the rows of the first matrix by the columns of the second matrix. I want to do an example now. So let's say I'm multiplying those 2. All right. My battery is dying. So let me plug this thing in. Don't move. So I'm gonna pause the video and plug in this thing. Don't move, guys. Boom, 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 boom. All right, guys. All right. So how do we do the multiplication now? So everybody pay attention, right? So I'm saying to you, we use the rows of the first matrix and we multiply them by the columns of the second matrix. All right. And it's a matter, how do we know which row and which column to use? All right. So let me go step by step. I'm going to actually use the markup here. All right. So I'm going to be using the rows of the first matrix. So to show that I'm using the rows of the first matrix, I put a line across here. And to show that I'm using the columns of the second matrix, I put a line down here. All right. So what is going to happen is that I'm going to be multiplying first for one at a time this row by this column to get this value. All right. And then I'm going to multiply same row there by this column to get this value. And then I'm going to multiply this row by this column to get this value. And then I'm going to multiply that same row by this column to get this value over here. All right. But how do you reason it out without actually trying to know? All right. Let me show you a reason it out. So you don't have to like memorize. You can actually work it out. All right. Watch this now. So I know that I'm using the rows of the first matrix and the columns of the second matrix. I know that. So let's focus on this first element right here. Now, that first element that I want to get. Now, let me start first. Now, a 2 by 2, this is a 2 by 2 times a 2 by 2. That's what we have. It is possible because the number of columns and the number of rows in here match. And the resulting matrix is going to be a 2 by 2. So that's why my answer here is a 2 by 2. I just put in the letters A, B, C, and D to show that I'm trying to work out the value of A, the value of B, the value of C, and the value of D. My resulting matrix is a 2 by 2, which is what I've set up here. So I've set up a 2 by 2 matrix there. All right. All right. So back to this now. Trying to explain it for the first time. All right. So this first element here that I want, this first element is actually an element in the first row and the first column. That's where that element is. First row, first column. And so to get that element, I have to multiply this first row by this first column to get the element A. So this first row, I'm calling it R1, and this first column, I'm calling it R2, column C1, column C1, column C1. So to get this element, this is a R1, C1 element. So to get that element, I have to multiply row 1 that I'm using by column 1 that I'm using. And I multiply along the row, down the column. What do I mean by along the row, down the column? Let me show what I mean by along the row, down the column. What I mean by along the row, down the column is that I multiply the first element in the row by the first element in the column, and I multiply the second element in the row by the second element in the column. So you see, I go along the row, down the column. So I like to say first element by first element, second element by second element. And that's how you do all of them. First element by first element, second element by second element. All right, let me continue on the slide now to show you what happens. All right. So the first element A, as I said, is a R1, C1 element. All right. See, so those are the rows. Those are my columns. All right. 2 rows and the 2 columns that I'm using. So my first element A really is a R1, C1 element. But understand that it is in the first row and the first column. So to get that element, it means I have to multiply the first row, which is 0, 1, by the first column, which is 6, which is 4, 6. So let me show that down here now. For the second element, let's look at the second element. The second element, I think I filled out all of them already. So the second element here now, look at it. This element here now, right, is a first row, second column element. That's why it's R1, C1. So to get that element, I have to multiply this first row and this second column to get that element. All right, that's what I have to multiply to get that element. All right, let's go in step by step. Then the C now is R2C1. Why is it R2C1? Because it is in the second row and it is in the first column. So to get that element, I'm going to multiply the second row times the first column to get this element down here, the R2C1. All right. And then the last element is a second row, second column element. See there? Second row, second column. Why is it called second row, second column? Because this element is in the second row and it is in the first column. Second column, sorry. Second row, second column. So to get that element, I'm going to use this second row and this second column to get that element over here, this last one. That's why it is called R2C2. So it's basically telling you the position of the element that you're trying to get. Is also telling you which row and which column you have to use. All right? So I'm going to do them now. I'm going to actually do them now. So already know. The first element, which is R1C1, the first one, meaning that I'm using R1 row and C1 column. I'm going to put them side by side and show you. See them there? So I'm using the 0, 1 row and the 4, 6 column. Everybody understand that before I move on?
Yes, sir.
Everybody understand that?
Yes,
Yes,
sir.
Yes, sir.
Then I'm going to multiply the first element in the row by the first element in the column and the second element in the row by the second element in the column. So it's first element by first element, second element by second element. See it here? Let me show you. First element by first element, so this times this, and then second element by second element, and you add the values. So 0 times 4 and 1 times 6. Give it the element that is coming right here, which is same that element. All right, so look at it. So 0 times 4 and 1 times 6. That works out to 6. So it means that the R1C1 element is 6. I'm going to put it in the final matrix now. It's supposed to be 6. But you understand that so far?
Yes, sir.
Good. Then I'm going to do the second element now, which is the R1C2. That element is R1C2 because it is in the first row and the second column. So I have to use the first row and the second column to get that element, R1C2. See there? That's it, R1C2. I have to use the R1 row and the C2 column to get it. 0, 1, 5, 7, I have to multiply. Same thing. First element by first element, second element by second element. First element in the row by the first element in the column, second element in the row by the second element in the column. Bam. So it's 0 times 5 and 1 times 7. That equals 7. So that R1C2 element is equal to 7. That element is 7. So far, so good?
Yes, sir.
Good. The other element we're going to do now is R2C1 element. Row 2, column 1. Row 2, column 1. So because the element I want now is row 2, column 1. That's the element down here. This element. Row 2, column 1. I have to use row 2 and column 1 to get that element. Right? So depending on where the position is telling me the row and the column that I have to use. All right? The only thing I want us to leave is that I'm using the rows of this one and the columns of that one. All right? So back to this now. I'm using 2, 3, and 4, 6 to get that element. First element in the row by the first element in the column. Second element in the row by the second element in the column. So that's 2 times 4 and 3 times 6. 2 times 4 and 3 times 6. 2, 4 is 8, 3, 6 are 18. 8 and 18 is 26. So 26 becomes that second row, first column elements. I'm going to put it in the final set there now, final matrix there now. That's it, 26. Good. And then the last element now that I want is the R2C2. That element is in the second row, second column. So to get that element, I have to use this element we're talking about now. This element. That element is in the second row and the second column. So to get that element, I use this second row and this second column. Remember, always take the rows from this matrix And I always take the columns from this matrix. You use the rows of this matrix and the columns of this matrix when you're multiplying matrices. All right, so I put a line across here to show that you use the rows, to show that you use the column. Some teachers do this. Show you what some teachers do. Some teachers do like this. They put that. Some teachers do this. Some teachers circle the rows that they're using and circle the columns that they're using. Some teachers do it like that. All right, I don't do it like that. I just put a row, a line across here, to show that I'm using these two rows. And I just put a line down here to show that I'm using these two columns. That's how I do it. Same difference. I'm using the rows of the first matrix and the columns of the second matrix. So we're going to R2, C2 now. R2, C2. So R2 is 2, 3, and C2 is 5, 7. So I'm multiplying 2, 3 by 5, 7. First element by first element, second element by second element. So it's 2 times 5 and 3 times 7. 2 times 5 and 3 times 7. 2 5 is 10. 3 7 is 21. 10 and 21 is 31. So the last element there is 31. Bam, 31. And that's the final matrix when I multiply those two. But understand that?
Yes,
But
sir.
good?
Yes, sir. Yes, sir.
Yes, sir.
All we need to do is practice. Practice, guys. Practice and get it perfect. Now look here. This breakout that I did down here, I'm not going to do it again. I'm not going to do this again. I'm going to break it out this one time so you can see the steps. Going forward, I'm just going to look at the row that I'm using and look at the column that I'm using and work it out. So I'm not going to do this thing down here anymore. I just did it this one time so you can see the actual column, the actual row, and the actual column that we use. And you can also see that we use first element by first element, second element by second element. All right? That's all.
Sir.
So moving, yes?
I get it 31.
I'm going to get 31. 2 times
Yes, sir.
5 is 10. 2 times 5 is 10. 3 times 7 is 21. 10 and 21 is 31. See it?
Yes, sir. Yes, sir.
All right, beautiful. All right,
Sir,
so
my brain-
moving on now.
Yes, sir.
No problem, man. No problem, man. No yourself. All right. So another thing Stacey like to test about is that multiplication of matrices is non-commutative. Anybody know what the word commutative mean?
Goes anyway.
Commutative. What does the word commutative mean?
So like it's not the same as it like, let's say 3 times 6 equal to 18. So it's in a
Yeah.
different line, it could be 3 bracket 6 equal 18. It cannot be like that.
No,
sir.
no, that's associative. Commutative has to do with reversing the
Sure.
order. Has to do with reversing the order. So I think he's on the right track. 3 times 6 is the same as 6 times 3. This equal 18, and this still equal 18. That's with real numbers. So the multiplication of real numbers is commutative. Same thing with addition. 2 plus 5 is 7. If you switch them around and put 5 plus 2, it's still 7. So addition of numbers is commutative, and also multiplication of numbers is commutative. Write it another way. 3 times 6 is equals 18. And 6 times 3 is still equal to 18. That's a multiplication. So multiplication is commutative. The word is commutative. Addition. 2 plus 5 is 7. If I switch on the order word 5 plus 2 is still 7. So the addition of numbers is commutative. Division is non-commutative. And also subtraction is non-commutative. So these two are commutative. Commutative. When you reverse the order, the result is the same. Non-commutative example now. Non-commutative. Non-commutative. You know it's spelled non-commutative, whatever. So like division, watch this now. 6 divided by 3 is 2. But 3 divided by 6 is a half, 0.5. See, the result is not the same when you reverse the numbers. Same thing with subtraction. 6 minus 2 is 4, but 2 minus 6 is -4. So you see the result not the same. That's what I mean by non-commutative. So these division and subtraction are non-commutative. Additional multiplication are commutative. Now, what they're basically saying on this slide now is that matrices multiplication is, generally speaking, non-commutative. Meaning when you reverse the order of multiplication in matrices, the result is different. When you multiply 2 matrices and you switch them around, you're not going to get the same answer. Generally speaking, the only time you get the same answer is when the identity matrix is one of the matrices. So I times A equals A, and A times I is still equal to A. So only when the identity matrix is involved is the multiplication of matrices commutative. Otherwise, it is non-commutative. Another reason why it is non-commutative is the example that we did over here. In that, it was possible to multiply the 4 by 3 and the 3 by 2, but it is not possible when you switch them around. That's another way of proving that it is non-commutative, because if you multiply them one way, you're good. If you multiply them the other way, you're not good. It is okay one way, but not okay the other way. So that's another way of proving that multiplication in matrices is non-commutative. Generally speaking, when you switch the order of multiplication in matrices, the result is different. CXC like to test your knowledge of that as well. So they like to test your knowledge of if you know how the multiplication is possible. They also like to test your knowledge of the fact that matrices multiplication is, generally speaking, non-commutative. The only time it is commutative is when the I matrix is one of the matrices you multiply, as I just said, which is the 1, 0, 0, 1. That is the I matrix, the identity matrix. All right? So basically, that is it. So this slide is about that. That matrices multiplication is non-commutative. I think I showed it with an example. That is it. If A and B are 2 matrices, then A times B is not equal to B times A. So if I give you 2 matrices to multiply them and I tell you to multiply A times B, you can't write BA and expect to get the marks, because the answer is going to be different. If you multiply them in the right order that I asked to multiply them, because if you switch them around, the result is going to be different. And CXC have asked in the past multiple times to prove that multiplication in matrices is non-commutative. If they tell you that, all you need to do is switch around the order of the multiplication and prove. We're going to see those questions, you know. We're going to come up on those questions and we'll see. But I want you to understand the word from now. Non-commutative means that when you switch around the order of the multiplication of matrices, the result is different. The result is not the same. And so it is non-commutative. If it was commutative, then the answer would be the same. Let's look at an example. Here I'm multiplying 2 matrices, a 2 by 2 and a 2 by 1. That multiplication is possible. Why? Because a 2 by 2 times a 2 by 1, the two of them have the same number of columns. Same number of columns in the first one as there are in the second one. So the multiplication is possible. And the result is going to be a 2 by 1. That's why my result is a 2 by 1 right there. All right? And how do we carry out that multiplication? Same thing. Rows in the first matrix by the 1 column. We only have 1 column. Rows in the first matrix by the 1 column. Let's look at how we get the values now. Pay attention. How we get the values. It is first element here, which is really this. First element here, which is really that. Look at how we get it. 3 times 2 is 6. 1 times 3 is 3. First element by first element, second element by second element. Let me use some color code and do it and show you. Let's use some color code. So I'm going to go 3 times 2. 3 times the 2, give me 6. This is a different color now. Let's use blue. Let's use blue. And then 1 times 3, give me 3. And them add to 9 right there. So them add to 9. Let's use another color now for the second pair. Second row by the one column now. Let's use a different color. Let's use green. Let's use green and yellow. So now it is 7 times the 2. 7 times the 2, give me the 14. And then let's use the yellow. And then 4 times the 3, give me the 12. 4 times the 3, give me the 12. And then that's how I get my final answer here. But understand that? So that multiplication is possible. Let me erase all of that. Rows by the one column. 3 times 2 is 6, and 1 times 3 is 3. All right? And then for the other one, it is this row times the one column to get this value, to get these two. So 7 times 2 is 14, and 4 times 3 is 12. And they add to 26. That's it. So that multiplication is possible. But to prove the non-commutative nature now, non-commutative. Sorry. All right, to prove the non-commutative nature now, what will we switch them around? So we switch around the order and put the 2 by 1 in front. It is not possible. See there? 2 by 1 times the 2 by 2 is not possible because those two don't match. The number of columns in the first matrix is 1. The number of rows in the second matrix is 2. They don't match. And so that's all they write. It is not possible. There's no result from that multiplication. Are they good? But understand that?
Yes, sir.
All right,
Yes, sir.
good. All right, good.
Yes,
So
sir.
that is how we prove it. And we can actually use actual values and prove it. All right. Matrices notifications. I'm going to stop at matrices notification. Buddy there? Yeah. I kind of getting some bad weather. So the internet kind of chipping in and out. So far it's holding up. But if it cut off, just stay on, I'll log on back. All right. I want us to get to matrices notification. So matrices notification is just that they basically use letters to represent matrices. That is all it's about. They tend to use letters to represent matrices. All right. That's all this is about. The matrices are usually denoted by capital letters, and we can do these examples just to show you matrices notification I use. And we're going to do some equality of matrices. All right. So let's do these examples over here just to practice what all that we have said. All right. So I want us to do these two now. I'll do this question just to practice all that we have said. All right. So ready? So they give us these two matrices. A is a matrix 3, 4, 2, 1. And B is a matrix 2, 3, 4, 2. So these are two 2 by 2 matrices, both of them. So we can do anything with them. We can add them, we can subtract them, we can multiply them. Because they are the same size, right? And do anything we want with both of them because they are the same size. A and B. First part tells us that C is equal to A plus B. C is equal to A plus B. So talk to me now. I can just add the corresponding values to get C. A plus B is obtained by just adding the corresponding values, don't it? So I can just do it. 3 plus the 2 is 5. 4 plus the 3 is 7. 2 plus the 4 is 6. 1 plus the 2 is 3. What are good at that?
Yes, sir.
Beautiful.
Yes, sir.
Then part 2 wants us to subtract them, which is possible because they're the same size. D equals A minus B now. Subtracting them now. Let's just write the answer. So we're doing 3 minus 2 is 1. We're doing 4 minus 3 is also 1. We're doing 2 minus 4 is negative 2. And we're doing 1 minus 2 is negative 1. How that look? How that look? That look right?
Yeah.
Yes, sir.
All right. Now second, guys. Now second. All right, so far so good. Then E now is actually multiply them. So I'm going to practice the multiplication with E now. E now is to multiply the A and the B. All right, so for E, I'm going to multiply them now. Part 3 is to calculate E. So E equals AB. Which is to multiply them. So multiply the A, and you have to put a multiplication sign between them. You put them side by side, it means multiply. All right, so it's 3, 4, 2, 1 times 2, 3, 4, 2. And the columns of the second matrix to do a multiplication. All right, and now we're gonna write now a big 2 by 2 matrix. 4 values, 1 here, 1 here, 1 here, 1 there. But I can see that. All right, so let me do about this part. I think I missed that part. So I'm saying we're multiplying these two matrices. Let's do about this part. A times B. So the A matrix times the B matrix. So A is a matrix. 3, 4, 2, 1. So it's 3, 4, 2, 1 multiplied by 2, 3, 4, 2. So a 2 by 2 times a 2 by 2 is going to give you a 2 by 2. I'm going to draw a big 2 by 2 here so I can show you how I get the values. In fact, I'm going to draw it bigger. I'll show you how I get the values. I'm going to draw a big 2 by 2 that we're getting. I'm just going to multiply them and show you. I'm going to get a big 2 by 2. I'm just drawing it large like this so I can show you how we get those 4 values. 4 values. All right, let's use it out. Now remember, when you multiply the matrices, you use the rows of the first matrix by the columns of the second matrix. That's what you do. All right, so I'm multiplying those two. So ready again now. This first element here now that I want, it is in the first row and the first column. So to get that one, I have to multiply this first row by this first column. How do I do it? First element by first element, second element by second element. First element by first element, second element by second element. So let me go and do it now. So this first element here is actually going to be, let's put it back in purple. 3 times 2 is 6, and 4 times 4 is 16. Understand that? 3 times the 2?
Yes, sir.
Good. So it's 6 plus 16. That's the first element. Ready now. The second element now. Second element now is this one. Now this one is in the first row and the second column. So to get that element, I'm going to multiply this first row and this second column. That first row and that second column to get that element. All right? But understand that. Remember, it is first element by first element, second element by second element. Those are what we're going to multiply. First element by first element, second element by second element. So let's do it now. So basically then it becomes 3 times 3 is 9 and 4 times 2 is 8. That's it. But I go to that. But all right with that?
Yes, sir. Yes, sir.
Yes, sir.
All right, we'll come to this element now. This element
I cut
now.
out a bit earlier, sir. So,
Huh?
I cut out a bit earlier, sir.
All right, you
Earlier,
catch
sir.
on this next one because the same procedure. Let's pay attention. This third element now is in the second row and the first column. So to get that element, I have to multiply this second row and this first column. First element by first element, second element by second element. So it's 2 times 2 and 1 times 4 to get that element down there. Let's look at it. Putting in the values now. So it's 2 times 2 is 4 and 1 times 4 is 4. That's it. The last element down here now. This is in the second row and also in the second column. So to get that element, I have to use this second row and this second column. First element by first element, second element by second element. That's what I'm multiplying to get that last one. All right, let's look at it. So ready. 2 times 3 and 1 times 2. 2 times 3 is 6. 1 times 2 is 2. So my final answer is 22, 17, 8, and 8. But understand that?
Sir.
Yes, sir.
All right, let me show you something now, which is not a part of this question. So for the question say, show that matrices multiplication is non-commutative. Suppose a part 3, them say, hence, show that matrices multiplication is non-commutative. So they ask you to do this, and then so suppose them put another part of the question, part 3, part 3, part 3B. Let's say this is part 3A, and this is part 3B. And part 3B says, hence, let's put it in something now. Show that matrices multiplication is non-commutative. Good question, say that. What are you going to do to show that matrix multiplication? Remember, I said it's a AB, you know. It's a E equals AB, you know. It's a really AB, you know. AB. That E equals AB. What are you going to show that matrix multiplication is non-commutative? Hence, use this so we have to show that matrix multiplication is non-commutative. Anybody can tell me what you would do to show that it is non-commutative? Matrices multiplication is non-commutative. Anybody have an idea what you would do?
So you would reverse it?
Just reverse it. Just multiply the B times A and show so you get something different. Right? So you can say no. B times A would be, you put the B first now. 2, 3, 4, 2 times 3, 4, 2, 1. Now what's the beauty of it now? What's the beauty of it now? Remember say AB are the suppressor, you know. What's the beauty of it now? We're going to show it fast. Watch this. I'm multiplying the rows of the first one same way, but the column of the second one same way. And I know that my answer is still supposed to be a 2 by 2 matrix with 4 values. I'm going to work out the first one first using this row and this column. And let's see what we get. All right? I'm going to get 2 times 3 and 3 times 2. So I'm going to get 6. I'm going to get 6 plus 6. See that? Which is 12. So this is going to become 12 something, something, something. Now watch me now. I don't have to go any further, you know. Since this first value is different from this first value, I don't have to work out these. I don't have to waste time work out the rest of them. They are already not the same from that first element different. See that? So I can just write here, so. Since the first element not the same, I can simply say not equal to AB. Not equal to AB. Therefore shown. I have shown it that it is not commutative by showing that the BA is not equal to AB. Because the BA first element different from the first element in AB. So I don't have to waste time and work out the rest of them. Once one element different, it means that the matrix, the two matrices is different. Everybody understand that?
Yes,
So if you
sir.
ever get this question, that's all you need to do. You don't have to waste time work out all of them. They have to give you the marks. Because from the first element different, it means to them different. But understand that? But good?
Yes, sir.
All right. So we'll
Yes,
squeeze in a little.
Sir.
Oh, just squeeze in a little question now. Watch this now. Pay attention now. The last part now, right here, is to do F equals A squared. So doing F part 4 now. We're doing F equals A squared. But pay attention. F equals A squared. So that really is the A matrix 3, 4, 2, 1. So that will be equal to 9, 16, 4, 1, right? Square the values. Agreed? But I get that?
Yes, sir.
Yes, sir. No, sir.
Huh? Somebody say no?
Yes, sir.
Who say no?
What answer? Oh, sir, me get it.
Say agree. Everybody agree with this?
Yes, sir.
All right. I don't want anybody to agree with this because this is wrong. So me make sure showing the mistake first. I mean, I tell you now that this is wrong. Matrices multiplication is a process. You cannot just square the values. You have to multiply the rows by the columns. So you see the A squared that they give you right here is actually equal to A times A. You cannot just square the values. So this is a big wrong bang. So you can't say Mr. Sean ever show you the mistake and tell you, say, don't do that. If you ever say A squared, you cannot just square the values. Matrices multiplication is a process where you multiply rows of the first matrix by the columns of the second matrix, and you have to carry out the process. You cannot just square the values. The answer is this is wrong. Wrong. So make this be the last time anybody do anything like this. You get me? So I'm show you what naturally a lot of people would do. This is what a lot of people would do naturally. Because that's what we're used to. And that's what your brain first tell you to do. It is wrong. So I show you the mistake before you even make it. So when you get it in the classroom, no one see nobody do this foolishness ever again. It is wrong. A squared means A times A. So you have to put the A matrix beside it. The A matrix, and you multiply the rows and the columns. So let's do the right thing now. So about this quick before nobody see it. It is so wrong. You don't even want nobody to see it too quick and make it go into them brain too much. Okay, it is so wrong. All right? So I'm going to show you the mistake before me even teach you the right thing. So let's go. Remember, A squared really means A times A in matrices. Matrices multiplication is a process. You must carry out the process. So it means that they put the A by beside itself. So you put the 3, 4, 2, 1 beside the 3, 4, 2, 1. And you multiply the process, which is the rows of the first matrix times the columns of the second matrix. You're going to see that the answer is not going to be the square of the values. Not. It's going to be equal to a big 2 by 2 matrix again. 4 values. Let's go through it one more time. First element here is first row, first column. So use the first row and the first column. First element by first element, second element by second element. go through the process. No shortcut with multiplication. All right. So it's 3 times 3 and 4 times 2. 3 times 3 is 9. 4 times 2 is 8. So this is the first value different already. Our first value we're getting is 17. You all a while ago said it would be 9. I square the 3 and get 9. This is actually 17. 3 times 3 and 4 times 2. Then this element here now, it is in the first row and the second column. So to get that element, use this first row and this second column. First element by first element, second element by second element. 3 times 4 and 4 times 1. 3 times 4 and 4 times 1. All right, to get this element. 3 times 4 and 4 times 1. All right, 3 times 4 is 12 and 4 times 1 is 4. Getting 16 there, which is a squared value. All right, but that is it. Then this element here now, it is in the second row and the first column. So to get that element, we have to use this second row and this first column. First element by first element, second element by second element. First element by first element, second element by second element, like a song, sing it every time. First element by first element, second element by second element. You multiply in matrices. So it's 2 times 3 and 1 times 2. 2 times 3 and 1 times 2. 2 times 3 and 1 times 2. 2 times 3 is 6, 1 times 2 is 2. That element works out to 8. Then this last element now, it is in the second row and the second column. So to get that element, we use this second row with this second column. First element by first element, second element by second element. 2 times 4 and 1 times 1. 2 times 4 and 1 times 1. 2 times 4 and 1 times 1. 2 times 4 is 8 and 1 times 1 is 1. So the final value there is 17, 16, 8, 8, and 9. So it is not equal to the square that we put a while ago. While ago we put 9, 16, 4, and 1, which was wrong. So you see that, put 9, 16, 4, 1, which is wrong. All right, so you see that that is wrong. So this is the correct answer. Everybody good? But understand that?
Yes, sir.
Yes, sir.
Yes,
Make it
sir.
stick. So when it's a square, you have to multiply the matrices side by side and go through the process. You cannot just square the values. All right, very good. All right, let's move on. I think we're gonna finish on this slide. I don't want us to go past this. Equality of matrices. We're gonna finish on this slide. Equality of matrices is basically saying if two sides of an equation in matrices are equal, then it means that the corresponding values are equal. That's all it means. So when you want to compare two matrices, you just basically bring the matrices so that one side, if you have an equation of matrix, if you have a matrices equation, and you can bring the two sides to become the same, then you can just equate the values. All right. So something like this, in simple terms. If two matrices are equal, then their corresponding elements are equal. So it's a method that we use to solve matrices equation. We bring the two sides of the equation to be equal. And when you bring the two sides to be equal, then you can equate the corresponding elements. So in this example, which they won't give you an exam, I'm just showing you this to demonstrate what we're saying. The A will be equal to 1, the B will be equal to 2, the C will be equal to 3, and the D will be equal to 4. So when two matrices are equal, their corresponding elements are equal. So how do we apply this to a question? Now watch this now. Bam. Look at this. Now suppose I want to solve that equation for the x and the y. What I can do is reduce this side. Reduce this side to a 2 by 2 matrix and then equate the values over here. Right? Or put another way, we can use what we know about matrices multiplication. Watch this now. Watch this now. What do I know about matrices multiplication? I know that this row times this column is equal to the 7. See that? I'm using another color another color, I know that this second row times this second column is equal to the 30. So I can do that. But understand that? So I can multiply the corresponding rows and columns to get what I would have over on the right side. That's equality of matrices. That's an equality of matrices question. All right. So I can set it up like this in the example. So let's set it up like this. So that example is 2, 1, 3, 4 times x, 2, 3y. And we are saying that equals 7, 10, 18, 30. Right? So I can basically say, as I said, I can say, use what I know. I can say this row and this column equals 7. And set that up. Here, the 2, 1 times the x3 is actually equal to 7. And that gives me one equation. Right? That tells me, this tells me that 2 times x and 1 times 3 equals 7. See here? 2 times x is 2x, 1 times 3 is 3, equals 7. And then I'm solving this for x. Here over the 3 and subtract it, we get 2x equals 4, and then divide by the 2, we get x equals 2. That's my x value. Going further, I can also use a 10. Let's use the 10 with the y. Watch this now. So I can use a 10. Watch this now. For the second one, I can use a 10. And say, all right, the 10 that I'm looking at there, the 10 right here is obtained by multiplying this row by this column. Right? And I can set it up. And say, all right, the 2, 1 times the 2y equals the 10. And then I work it out. 2 times 2 and 1 times y equals 10. So 2 times 2 is 4. 1 times y is y. That equals 10. And I carry over the 4 and subtract. I get the y equals 6. I'm done. I could have used these values too if I wanted, you know. I would just do them for good measure. Let's just show you for good measure if we wanted. All right. Could have used those values as well if I wanted. So let me just show you quick. I could have used those values if I wanted as well. I could have instead used, for example, this times this equals the 18. Right? And I would have gotten 3, 4 times x3 equals 18. And that would work out to be 3 times 4 and 4 times 3. That would be 3x plus 4 3s 12 equals 18. Subtract the 12, I get 3x equals 6. And then divide by the 3, I get x equals 2. Same as x equals 2 up here. I also have the option of using the 30. Let's use the 30 and see to get the y. If I'm using the 30 is this row times this column equals 30. So it's 3, 4, and 2y equals 30. Let's set it up. 3, 4 times 2y equals the 30. See there? 3, 4, 2y equals 30. And then again, I work it out over here. So it's 3 times the 2 and 4 times the y. equals 30. 3 times 2 is 6, plus 4 times y is 4y equals 30. Subtract the 6 first. 30 minus 6 is 24. So 4y equals 24. And divide by the 4. 24 divided by 4 is 6. So again, you see y equals 6. Same as y equals 6. That's equality of matrices, my friends. All right. So I think I did it on the slide, did I? Yeah, see there? Did it on the slide with the 7. And so on the slide, I did the 7 and the 10. And that's how we got the x equals 2 and the y equals 6. But I just worked it out on the right side fully for you, using all 4 options that you had for the question. All right, guys, I think I'm going to stop it there for today. I'm going to stop it there because I'm going to start back tomorrow's class with transposition, and we're going to go into these tools that we use in matrices to find things, to find inverse, determinant, inverse, all these things, using inverse to solve equations here. I'll do all of these things tomorrow, guys. All right, and then we're gonna finish off with that. Yeah, singular matrix. Yeah, we're gonna finish off with singular matrix. And get some examples. All right, this is tomorrow. Okay, students, that's it for today. We shall pick it up back right here tomorrow. Right here. We start back tomorrow.
All right, sir.
Position, I will take it from there. All right.
Yes, sir.
Everybody good?
Yes, sir. Thanks for the class.
Huh?
Thanks for the
Thank
class.
you.
Yeah, man, no problem. No problem.
Bye, Dad.
Bye, my princess. We shall talk some more later, okay?
Okay.
All right, babes. All right, I'm gonna end the class for everybody now. Bye. See you all tomorrow.
Yes, sir.
Bye. All
Yes, sir.
right. Okay, bye.